All right, everyone. Welcome to this next episode of Quantum Computing Podcast. In the last episode, we were on page 9 and we had actually just finished and we were moving on to page number 10. So let's continue that. Let's do that in this episode. All right, so what's on page number 10? All right, so page number 10 starts with the new section, the algebra of complex numbers. So the geometry of complex numbers will be introduced in the, next section. So this section actually starts by asking the same questions that we had encountered, that what actually is an imaginary number, or what does it even mean that square of an imaginary number I is -1? What does it mean? So let me remind you that we introduced this notation of imaginary numbers to make our lives easier. Okay, so if we just assume that such a number exists, even though, as I pointed out, that from our current understanding, the square of any number cannot be a negative number, let alone -1. So but let's assume that, such a number exists, because in quantum mechanics and in many other fields, we encountered a situation where a square of something needs to be or could be -1. So if we just assume, such a number exists, we know it doesn't exist right now, but in future maybe there is some advancement in math, algebra, or whatever, and we would come up with or we would know such a number. Okay, so right now let's assume and move on and do more advanced things. So that's what imaginary number is. And what is it? Yeah, so this is that if you just look at complex number more carefully, and as you know, complex number is an expression. It's made up of real number and imaginary number. But if you just think carefully, it's nothing but it's an ordered list of two real numbers. So if C is A plus BI, then A and B are real numbers. So this section actually introduces this new notation that what if we, rather than saying A plus BI, what if we introduce this new notation where A and B are real numbers? It's an ordered list. It's not a random list. It's an ordered list, and maybe we can start referring to complex numbers as basically an ordered list of two real numbers. So let's say if it's just a real number like an A, which can be written as A plus 0i. 0i means it has no imaginary part. You can still use this notation. You can say A0. Similarly, if you just want to use I, then I can be written as 0 plus I, or 0 plus I. So basically it can still be noted as 0 1. So this notation is still useful. And another reason to introduce this notation is now you have like a formula for multiplication. Rather than doing this lengthy multiplication, maybe you can now just use this formula. Okay, so if there are two complex numbers, order list of A1 B1 and order list of A2 B2, then you can just apply this formula for multiplication. And a couple examples that it actually works. And what does it say? It notes that multiplication is rather strange, right? It's not a component-wise multiplication that you would be assuming or expecting, but it's okay. It's still a formula. Nothing noteworthy. All right, so let's do this example. Okay, so if C is an ordered list of 3 and -2, and C2 is an ordered list of 1 and 2, then if you just apply this formula or a rule, then you would arrive at this answer. You know what? Let's do this with our old way of multiplying. these two complex numbers and see if we come with the same answer. Okay, so C1 is 3 minus 2, okay, which is 3 minus 2i, and C2 is order list of 1 and 2, which is 1 plus 2i. So until now we were doing this multiplication C1 multiplied by C2 as this 3 minus 2i into 1 plus 2i, right? So that would be 3 into 1 plus 2i minus 2i 1 plus 2i. So this was this would result to 3 plus 6i minus 2i minus 4i square. So 3 plus 6i minus 2i is 4i minus 4i square is minus 1. So 3 plus 4i minus 4 into minus 1 would be plus 4. So that is 7 plus 4i. And that's exactly what we get here, 7 plus 4i. And this uses this notation, I mean formula, a1 into a2 minus b1 into b2, and second number, real number in this order list is a1 into b2 plus a2 into b1. And we can actually use this exercise to do this. Okay, all right, so done with this example. We know the numbers match. Let's do this exercise. Okay, so the exercise 1.2.1 is right here, that two complex numbers are given and we want to calculate their product. And for this one we are going to use this new formula rather than doing our old way. Okay, so you have that example. So let me write this down here first. C1 is an ordered list of minus 3 and minus 1, and C2 is an ordered list of 1 and minus 2. So C1 into C2 is equal to, well, you know what, let's write down this formula here as well. It's A1 A2 minus B1 into B2 and A1 into B2 plus A2 into B1. And for this, this is A1, this is B1, this is A2, this is B2. Yeah. So yeah, A1 into A2 minus 3 into minus 1 is minus 3, minus B1 into B2 is gonna be 2, positive 2, but the minus sign is coming from this formula. A1 into B2, A1 into B2, which is positive 6, plus A2 into B1. So A2 1 into B1 is minus 1. So minus 3 minus 2 is minus 5, and 6 minus 1 is 5. So here is your answer. And if you look at what I used to do, and yeah, I understand I could have skipped a couple steps here, but it was still lengthier, longer than this one. So it's a good, nice notation. But you know what, before we get super confident, let's check our answer of this exercise 1.2.1. Yep, minus 5 5 minus 5 5, right? Yeah, so this answer can be converted, although exercise is not asking for us to do that. But if we just want to convert it to our old way of writing complex number, then this just translates to minus 5 plus 5i. All right, just for fun. All right, where we are. Yeah, so almost 10 minutes and we just finished this exercise. So you know what, let's end here, and in the next video chapter episode, we are gonna start from here and see if we can maybe knock off a couple pages. All right, thank you.